Hurry up, hurry up, hurry up. Thank you. See, as soon as what my suggestion is, as soon as the lecture is over, you have your tiffin, and if you have time, then you go out, especially the boys. Don't go outside and then come inside and then have your food. हो गया?
टेंशन ना तुम लोगों को। तो पहले यहाँ खड़े होकर टाइम पास करते हो हैं, पर टीचर आती है तो फिर आप लोग यहाँ उधर टाइम पास उधर खड़े होकर फटाफट 2 मिनट तो बाकी ब्रेक एक बार मिलेगा ना अभी
बोल के देखनी है भाई तो अरे मैं खुद बोला ये तो बोलेगा ना तो अच्छा नहीं होगा
कसम से बोल रहा हूँ मैं बस नहीं है
और उससे और एक बोला ना मैं गंदा बोल दिया गंदा बोल दिया
कौन
एक बोल स्कूल वाला
That's one down. That's 50 down one. Yesterday we were talking about solenoid.
yes
So I'm sure all of you have realized what is a solenoid. It is nothing but an electromagnet. Okay. And how is a solenoid made? How can we make a solenoid? By coiling
electric wire.
yes, conducting wire in the shape of a cylinder. So suppose you are taking a copper wire, an insulated copper wire, and you are winding it around any cylindrical object, and you have to also connect it to a source of current. Okay, a source, like for example, it could be either directly from here, or obviously it could be a cell or whatever it is. So the moment you connect it, what happens is there's a current which is flowing through, and when the current is flowing through, this part obviously becomes, or it behaves like a magnet. Okay. The moment we shut it off, what happens? It loses its magnetism. Is that okay? Has everybody followed? Clear? And how can we make out the direction of the magnetic field? How can we make out the direction of the magnetic field? There is a magnetic field, no? So this is a magnetic field which is developing. How do I know whether it is this side or how do I know that is that side?
Circulation.
Depends upon the clock phase rule. Okay, so if it is moving in a clockwise direction, when you look at it from this side, suppose the winding is in the clockwise direction, what does it indicate? Is it north or south? Remember that N and S which I wrote? S, south. So it will be south because you have to look at the tail part of the alphabet. And if I look at the other side, and if I see that the coiling is on this side, then obviously it is anti-clockwise, then it means it is the north. So by looking at the face of the coiling, either this side or this side, if you look at it, then you can easily make out whether it is the north or the south. Is that okay? Clear? this basically is a pin, right? And here we have a nail and a copper wire, which we have one coil. Is this a magnet? No, it's definitely not a magnet. But let us see now what happens if you connect it. Did you see that? Do you see? It's a magnet. It's of course a very weak magnet because I'm using a 1.5 volt battery. So if the amount of current is more, then we just make out that the magnet is. This is just a demonstration to show you that this is a solenoid, as a simple solenoid. So when you're talking about an industrial solenoid, this nail piece is a huge armature core on which you are having many coils of copper wire. So that develops it automatically. Now here this basically behaves like what? It is behaving like a bar magnet. Okay. So if you're actually having a compass needle and if you weight it on either side, you can make out which part of it is repelling and which part of it is attracting. If it is attracting towards a particular pole, then we know that it is either the south or the north. If it is repelling, then you know that it is the right pole. Okay. So that is basically a demonstration to show you how a simple solenoid is now going to be acting like a bar magnet. Is that okay? Okay. Unfortunately, this, because it's a very thin wire, if I keep it on for a very long period of time, that entire wire is getting heated up. So that's why they say that you have to use an insulated copper wire. You can do this at home. You can take any nail or whatever it is. If you're having insulated wire, wrap it around and use either a cell or you can have two of them together, 1.5, you can multiply by 2. You can keep two sets together and see whether it behaves like a magnet or not. Okay, so far we are okay. Is that okay? Come to page number 201. Yesterday I have asked you to also draw the solenoid. Now, it is very important for you to understand the solenoid because whenever we draw the magnetic field, I'm just drawing a few coils for you to understand. Many of you tend to take the magnetic field away from the coil. No, magnetic field lines are always from inside the solenoid. So how are we going to draw? Okay, just draw this part of it and leave it. Look at the board. Let us see how we are going to complete the diagram. We are going to draw a few coils and leave it as it is. Then you start drawing your magnetic lines of force, starting from the inside. Because inside the solenoid, we see that the magnetic lines of force are all uniform. Then what happens? You are going to see on either side. Okay, so one side of course behaves like a north and the other side behaves like a south. So if it is the north, show that the magnetic field lines are going away. They are going away. If it is the magnetic south, it's coming. Okay, magnetic lines of force are coming inside. Okay, once you have completed this part of it, then you can complete your circuit. So what will you put? You can have many of them. You can have the key and show the direction of the current. Then we don't get the current. Okay. What happens is if you start drawing the connection and then you may not have place for the magnetic lines of force, don't do that. So what is the first step? What do you do? Draw only the coils. Leave it halfway through. Just leave this halfway through. Then you draw the magnetic lines of force. Okay. Once you have completed this part, then you show the connection. Then it will be your base problem. Is that okay? Clear? Okay. Now, why and where are we going to use such type of electromagnets? Are these electromagnets so useful that we have to actually create it? What is the difference between a permanent magnet and a solenoid? We said it is a temporary magnet. It's an electromagnet and it's a temporary magnet. Also, the strength of this type of magnet can be changed. How can you change it? By increasing the number of coils and also by increasing the current. Okay, by increasing the current, you can also increase the strength of the solenoid. So, having these two advantages is very useful in most of the industrial uses. For example, I don't know, you must have seen it on the TV or whatever. Suppose you have a scrapyard, okay, and we want to pick out, yes, we want to pick out only the metallic, the iron parts of it. So you have an electromagnet. So there is a disc which is an electromagnet. The crane will come into the dump yard and they switch it on. So then, of course, everything sticks onto it and then you can release it. Did you understand what I'm saying? A magnet is the one which is picking up pieces of iron. So how will you pick it up in a dump yard? Everything is mixed up. So let us say this is your electromagnet. It's coming into the dump yard. Okay. When you switch it on, what happens to this? It becomes a magnet. It's picking up all the scrap. You get it out and then you switch it off. Once you switch it off, what happens? You lose its magnetism and then it will drop. All the things, all the metal parts which is stuck onto it will get dropped out. So that is how you can separate out, okay, the magnetic material which can be present in a dump yard. Not only that, we are also talking about many different type of scientific equipment which is based on this. One of the simplest thing is your motor. Okay, where are the things that you can use a motor? Maybe a fan is a motor. Anything that's moving in your at home, washing machine has a motor, grinder has a motor. Do you understand? So all these, like for example, a hair dryer, a shaving machine, everything has got a motor. So we say that when you are having a motor, when you switch on, that is with the passage of electric current, it is getting converted into what type of energy? What? Very good. It is mechanical energy. So what does a motor do? Motor is nothing but a device which is bringing about a conversion of electrical energy into mechanical energy. Is that okay? Now before we go on to actually working on a motor and all that, I'd like you to come to the next page. Force on a current carrying conductor in a magnetic field. It's there. Now I'm just telling you to look at this. Did you see that horseshoe magnet? Did you all see that horseshoe magnet?
Yes.
Okay. Now so far we have been using only the right hand. What is this rule? Right hand and thumb rule. Okay. But now we have seen that whenever we are having a solenoid, one is we are having current. Second, we are also having a magnetic field. Third, if you get some other magnet close to that, it will have a repulsion. So that means to say there is a force which is also coming into play. For you to understand that, there's a very, very simple rule, and this is your Fleming left hand. Okay, so stretch out these 3 fingers of your left hand such that they are perpendicular to each other. Did you understand? Perpendicular. That means from the thumb to the forefinger it is 90 degrees. From the forefinger to the second finger it is 90 degrees, and obviously this one. So why are we talking about 3 different directions? X, Y and Z. Did you understand? So we have got X, Y and that's a Z. Okay, so there are 3 different axes. So if you remember this acronym, what is this acronym? All of you know that? You know this FBI? Just like CBI, we have got FBI. Okay, so that is a Federal Bureau of Investigation. So if you remember this acronym, it becomes very, very easy. So F stands for force, okay, and B stands for your magnetic field. I, of course, is your current. Having good, okay. So now, which finger is representing what? First, we'll start with F, which is the thumb. The first finger represents the direction of the magnetic field, and the third finger, the second finger here, represents the direction of the current. What I want you to understand is represents current is not current. You are going to use this word, it is indicating the direction of, similarly direction of. Okay, so once we are, sorry.
Everybody else feeling.
Come here, no. Where you want it?
On just this one. Just this one, not the others.
Keep one on, huh?
Yes,
One of them.
I'm keeping one up.
Which one you want to switch off now? Or you shift back, go back. Go, that's will be comfortable, go then. Anish, we don't want any extra comments in the class. Go, move fast. Anybody who wants to shift behind, go now. Not all of you, sit. You go.
Everybody, yes, no, everybody's really.
One of you will come, yes. Come here. One at a bench, huh?
Yes,
Boys, if you're moving, one at a bench. Anish, you sit there only. It's not shown there. That's okay. Okay? You're okay. You're not in direct line. Never mind. Let the bottle be there. No problem. The bottle will not run away anywhere. Okay? So what does it tell us? When we are passing current, pay attention now. When we are passing current, we have seen that there is a magnetic field. Okay? Current is given to us, which is I. Magnetic field is developed. And if there is a conducting rod kept in a magnetic field, it will experience a force. Okay, so let's see what this experiment is about. See figure 12.12. That's a very nice, simple experiment. Basically, what do we have? We have a horseshoe. Have you seen a horseshoe?
Yes.
Okay, maybe you must have seen it on.
Yeah.
You have seen it in the lab? Oh, excellent. Very good. Fine. If you have seen it, basically you have got, okay, north and the south. So similarly, we also have the force lines coming from which pole to which pole? Always north to south. This is, assume that this is north. Always it is in this direction. If you shift it here, it is again here. If you keep it like this, it's like this. Always from the north to the south. Okay, it's not going to change it. Now, next what is happening?
Ma'am, how can we identify like this?
It's given there, it will be there. And then S is always mentioned on the horseshoe magnet. Correct? So you are going to fix that in such a way, of course, that it does not fall. Next is we are going to keep a conducting rod. It's a rod, it's a conducting rod. That means to say you can pass current through it. Suppose the rod is like this, current is flowing in this direction. Okay. Now once again, did you notice that they have tied it up with something, and of course tied it up here, and there is a, so the current is passing from the positive terminal coming here, and it is going back again. So the circuit is complete. So when the circuit is complete, what is happening here? You have the current, which is I. Okay. It also develops a magnetic field. So how will we find out what is the direction of the magnetic field? This is the rod. Let us assume that the current is passing in this direction. There is a magnetic field which is developing around this. Which rule shall we make use of in order to find out the direction of the magnetic field? Very good. It is the right hand thumb. Okay. So I know the direction of the current. So keep the thumb in this direction. Thumb is showing you the direction of the current, and these curled fingers are the ones which is showing you the direction of the magnetic field. Okay. So we know here. So this is how it is going to be. Coming back to the experiment. Right. So the current is going in this direction. We are using the right hand thumb rule, holding it here. So we know that there is a magnetic field in this direction. The moment you switch it on, so obviously we must have a switch for switching it on and off. You will find that this rod makes a movement. There is a jerk, there is a deflection. Why is there a deflection? Because there is an interaction with the magnetic field which develops on this rod, and also there is a magnetic field which is running between the north and the south of the horseshoe. Have you followed? Imagine that this is the horseshoe and this is the conducting rod. The moment you switch it on, you find that there is a deflection. Okay? So the deflection can be either in this direction What happens if you change the direction of the current? Suppose you are changing the terminals here. Instead of the positive terminal here, suppose I put the positive terminal on this side. What happens now? The current is going in the opposite direction. So what happens now? The deflection will take place, but it is going to be in the other direction. That is, it is going to be in the opposite direction. Okay? So what does that tell us? That there is a force. Okay? Why is the deflection taking place? Because there is a force which is acting on this current carrying conductor. Because the moment you are having a current which is moving in a conducting wire or a rod, it develops a magnetic field, and there's an interaction between the magnetic field of the rod as well as the magnetic field of the horseshoe magnet. Is that okay? Have you all followed? Is it clear? Okay.
Force on a current-carrying conductor kept in a magnetic field. In 1821, Michael Faraday demonstrated that if an electric current is flowing through a conductor placed in between the poles of a horseshoe magnet, it experiences a force. Let us perform an activity to understand this concept.
See the animation, understand
Suspend
it.
a bare copper wire with the help of an insulated copper wire between the poles of a U-shaped magnet, as shown here. Observe the initial position of the copper wire, a good conductor of electricity. Now close the key to complete the circuit. We observe that the conductor shifts from its original position.
So it has moved this way. Can you see?
Now reverse the direction of the flow of the electric current.
What are we doing? Reversing the direction of the current. What will happen to the deflection of the copper wire? There will be a deflection, but it is in the opposite.
The conductor moves in the opposite direction. What happens to the conductor when the current is switched off? The conductor does not move. This indicates that no force is exerted on the conductor placed in a magnetic field when the current is switched off. While force is exerted on the conductor placed in a magnetic field when the current is switched on.
Did you get it? Yeah. Okay. So by looking at the animation, it becomes very clear as to how the deflection is actually taking place. Let's read it. Force on a current carrying conductor in a magnetic field. Are we ready? This is on page number 202. Okay. We'll start, Anish. Start.
We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor.
Stop. Pay attention to those two lines again. There are three terms which are coming up. Electric current, underline. Electric current is I. It produces a magnetic field, that is your B. And the field so exerts a force, that is your F. Yeah, underline. Okay, did you understand? Vicinity is in the close, in the near neighborhood. Yeah.
French scientist André Marie
Ampere. Once again, did you notice it was Ampere who actually found out this? And what is this Ampere used for? Unit of current.
Suggested that the magnet must also exert an equal and opposite force on the current carrying conductor.
So what is happening? Current carrying conductor, the magnetic lines of force is exerting an opposite force on this particular magnetic field. That's why it is capable of bringing about a deflection.
The force due to magnetic field acting on a current carrying conductor can be demonstrated through the following activity.
Read the activity.
Activity 12.7. Take a small aluminium rod AB of about 5 cm using two connecting wires suspend it horizontally from a stand as shown in figure 12.
Don't even listen to him. You do your work.
Place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. For this, put
Now,
the
in this particular experiment, how have they told? They are keeping it like this with the magnetic field upward. But in the demonstration that we saw, how was it? It is held this way. Did you understand? Either which way, however you keep the horseshoe magnet, remember that the magnetic lines of force are always from the which pole to which pole? From the north to the south. Okay, continue.
uh, for this put the north pole of the magnet vertically below and south pole vertically above the aluminum rod. Connect the aluminum rod in series with a battery, a key, and a rear string. Now pass a current through the aluminum rod from end B to end A.
Did you notice end B to end A in your diagram? In what direction it is coming? Is it connected from the positive? Look at the battery, positive arrowheads coming from that end, from the B to A end. Continue.
What do you observe? It is observed that the rod is displaced towards the left. You will notice that the rod gets displaced. Reverse the direction of current flowing through the rod and observe the direction of its displacement. It is now towards the right. Why does the rod get displaced?
Can you answer me? Why is the rod getting displaced? Why is this rod getting displaced? It experiences a force, correct? And it is, yeah, because when the current carrying aluminium wire is taking, what is developing around it? There is a magnetic field. So this is under the influence of the magnetic field of the horseshoe magnet, and therefore it experiences a force. Will you be able to write it properly? Yes? Put a Q there. There's a question there. They've asked you, can you explain why this deflection is taking place? The last sentence there. That itself is a question. Okay. Somebody else will read better.
The displacement of the rod in the above
Aram se pad, because each line is very important. Okay, no need to hurry up.
displacement of the rod in the above activity suggests that a force is exerted on the current carrying aluminum rod when it is placed in a magnetic field.
Underline that. Force is exerted on the current carrying aluminium rod when it is placed in a magnetic field.
It also suggests that the direction of force is also reversed when the direction of current through the conductor is reversed. Now change the direction of field to vertically downwards by interchanging the two poles of the magnet. It is once again observed that the direction of force acting on the current carrying rod gets reversed.
Okay, 1 minute. In the demo here that we saw, in the animation that we saw, what did they do? They have changed the terminals of the battery, positive and negative, and we have seen that there was a deflection. Is there any other way by which we can change the deflection here? Did you pay attention to what we were reading? See that last line. The last line that we read now, right here. Is there any other way by which we can change the direction of deflection? Reverse what?
Reverse the direction of current flowing.
एक तो current है. The other way is also change this. Okay, change the position of the north and the south. Okay, instead of keeping the north this way, if you keep it like this, then obviously the deflection is going to be changed. So there are two ways by which the deflection can get varied. One is by changing the direction of the current, okay, by switching the positive and the negative terminals. The other way of doing it is by turning or changing the position of the north and south with respect to the aluminium rod. Did you understand? Did you mark it there? Have you marked it in your textbook? Yes.
It shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Experiments have shown that the displacement of the rod is largest or the magnitude of the force is the highest. If the direction of current is at right angles to the direction of the magnetic field. In such a condition, we can use a simple rule to find the direction of the force on the conductor.
Okay, stop. If I keep it like this, okay, if I just keep it like this, will there be a deflection? Why not? And why?
Because it is not.
Yes, so what is important? Experiments have shown, did you notice the sentence there? What have the experiments shown? That the deflection is going to be maximum when all these two, what is this? Force is going to be maximum if your B and I, that is the magnetic field and the direction of the current, are perpendicular to each other. Did you understand? There will be a deflection even if it is not perpendicular to each other, but the maximum deflection will be got only when these two are perpendicular to each other. And for finding out what is the direction of the force, obviously we are going to use the next law, which happens to be what? It is the left hand Fleming's rule. It's a rule, it's not a law. It's only a rule to find out what is the direction of the force. Have you followed? We do not know the force. Did you understand? But we know the direction of the magnetic field. We also know the direction of the current. So when you are stating the law, look at me now, pay attention. When we are stating the law, don't talk about the force. We talk first about the magnetic field. We talk about the direction of the current. Then you will come to know the direction of the force. Is that okay? Ashkari? In activity 12.7,
In activity 12.7, we consider the direction of the current and that of the magnetic field perpendicular to each other
underline that word perpendicular to. It's very important.
and found that the force is perpendicular to both of them. That the three directions can be illustrated through a simple rule called Fleming's left hand rule. According to this rule, stretch the thumb, forefinger, and middle finger of your left hand such that they are mutually perpendicular. If the first finger points in the direction of magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor.
So what comes last? Thumb. What do we start with? Direction of the what field? Magnetic field. This one?
Current.
Yes, the direction of the current. If you know these two, then of course what is the direction of the force which can act. Is that okay? Very good.
Devices that use current carrying conductors and magnetic fields include electric motor, electric generator, loudspeakers, microphones, and measuring instruments.
Have you followed till now? Right. In your notebook, the first thing that we will write is about subheading, of course, is the force of the current carrying conductor. Okay. I want you to write down regarding Fleming's left hand rule. Statement of Fleming's left hand rule. So start from there. According to this rule, did you get it in your textbook there? Okay, take it down from there. According to this rule, textbook has it.
Where is it?
Hey, where are we talking? You did not pay attention. Then don't tell me. You will find out. Write it neatly. Don't scribble something. According. Mila Raj? Fleming's left hand rule, okay? Just below that. Did you underline?
According to this rule.
The master. Pay attention to the words that you are using. Perpendicular to, okay, fingers, etc.
in perpendicular to it.
Very good. That thing. If the first finger round that you will not write, you have to write that, no? You have to- if the first finger points, the data happening on the conductor. And ask one of you to give me the statement. So as you are writing, pay attention to what you are writing so that you learn it up right now in the class. Learn it up now only. Yeah. Ayush, finish writing or still writing? Can you read it please? Okay. Complete it now. Whatever you're writing, please complete. Arush, read what you have written.
Uh, According to this rule, its first finger points in the direction of magnetic field.
According to this rule, where what first finger?
Carries left hand.
अरे उसको कैसे स्ट्रेच करेंगे? Yeah, वहाँ से चालू करें.
Finger and middle finger of
Such that they are perpendicular to each other. वहाँ से चालू करेंगे.
and thumb gives direction of
Oh, right. That is very important.
and forefinger gives magnetic field. The central finger gives of induced current.
This is not induced current. Who said this is induced current? Induced current will be only for a generator. Thumb is showing a force. From where are you copying it down? You are writing it in your notes. But it's not given like that in the volume. You must have been seeing the right hand rule.
I'm in the left hand.
Children, there are two rules. One is a Fleming left hand rule which is used for motors. Okay. There is also another rule which is Fleming's right hand rule. Are you paying attention? This is used for a generator. Feed inside. Inside. Okay, this is used for a generator because we are inducing the current. Now, in your new volume of your textbook, that part has been deleted. Okay, though it is there in the volume, your right hand Fleming rule is not going to come into the picture at all because there is nothing there. In the earlier textbooks, we had motor, generator, all that was given in detail. So that is still there in our duty volume. Have you followed? All that you have to learn is I come and see. So we have to learn this and please write it from the textbook. It's clear in the textbook. Is that okay? Who can tell me the rule now? You want to try? Yes, try.
According to this,
No, don't look. According to the
rule, stretch the thumb, forefinger, and middle finger of your left hand,
uh,
and
in such a way
in such a way they are mutually perpendicular,
to each other, okay. Such that
such that the forefinger is the direction
shows the direction.
of the magnetic field.
Ah,
The second finger shows the direction of the current, and the thumb shows the motion of
that
the force.
direction of the force or direction of the motion. Did you understand? I think it's not a very difficult one. Only thing is pay attention to the different words that we have used. Okay, next. Now if I'm asking you a question, now that we have got it, suppose I want to increase the deflection. क्या करना पड़ेगा? Interchanging will change the direction of the deflection. I'm saying if I wanted to increase the deflection. What will you say? See now the deflection. Look at me. This is the magnet, horseshoe magnet, and this is the conducting rod. There's a deflection taking place. If I want to increase the deflection, it's what? Like that. So what will I do? What should I do? What will I change? Think of a solenoid. What is happening in a solenoid? What we have increased the number of coils. What like similar to that? What can we do here? We want to bring about more interaction between these two. So what should we do?
Battery current.
Yes, we can increase the current. Okay, by increasing the number of cells. Then current is more, so obviously battery, the magnetic field is also more. What is the second thing that we can do? There's no coil. There's no coil at all here. Coil nahi hai. In a solenoid there's a coil. What else can we do?
Stronger magnet.
Very good. You can use a stronger magnet. Did you understand? Okay, here instead of having only a simple magnet, you can use a stronger magnet. That is where our electromagnets come into play. We can increase the strength of a magnet by having an artificial and an electromagnet. Did you understand? So how can we increase the deflection here? By increasing the strength of the magnetic field. Second, by increasing the current here. And the third one is also by increasing the length of the rod. Is that okay? Come on, right now. How can we increase? Yeah, this is the question. How can one increase the deflection? Okay, I know which way it is.
It's like this, I can change it in any one direction.
I can change it in any direction. Use the direction I can set. The direction I can use the direction. This is perfectly alright, but what you said was not correct. Okay. I want 3 points there. Write down all the 3 points. Sorry, what did I say? Deflection of the aluminium rod. Deflection of the aluminium rod in the experiment. Deflection of
Aluminium rod
in the whatever the experiment of the aluminium rod in the experiment. Which experiment are we talking about? Yeah, what experiment?
This is the second question, right?
Hmm. What are the 3 points? First one, increase not the flow, increasing the strength. First point, increasing the strength of the current. Second point, by using a strong horseshoe magnet, or by increasing the strength of the magnetic field by horseshoe. That way also you can write. Raj, you listen to what I am saying. Now you are peeping there, again you are missing out what I am saying. Whatever you hear, you take it down. Then whatever you have missed out, you can copy it down later. And the third one is increasing the length of the conducting rod.
Increasing the length.
Of what?
Conducting rod.
Is this okay? Did you all understand? Okay. Now, the confusion was in the diagram which is given in the textbook as to what this will not change. Either which way, if I keep it like this or if I keep it like this, if I keep it like this, these three will still remain at 90 degrees to each other or perpendicular to each other. Have you followed? Now, in this direction, if at all you want to talk about this one, if I know the direction of the current, okay, and if I know the direction of the magnetic field, I can do it in any which way. Okay. Suppose all of you please keep it this way. So I'll say, suppose the direction of the current is from west to east. Now, which is west, which is east? Let's write down this now. North, south, okay, and west and east. And then FBI. So suppose I say the direction of the current is from west to east, and let us say yes.
In the experiment, a solenoid is used because there are coils of wire in the
When
on the rods. There are
that is not a coil as in, that is just to hold the rod like that. Just one rod with one wire they have put it so that it is hanging from it. Otherwise it will fall down. A solenoid will have so many coils like what I have here.
But the current is flowing.
Correct. Without the current, how will you have? How will this magnet, this aluminium? ये देखो यहाँ से wire है. The wire is connected here so that the current has to flow na. Where is the coil here? You're saying on this there are coils?
no
Then
rod.
yes, obviously the rod has to be connected here, no?
Rod is not a rod, not
There's a rod.
That is a stand. Now, how will this stand now here? I have not drawn a stand right here. This is not a coil. This is only to hold it together. That's all. That's not a solenoid. Yeah, that's not. See, suppose this is a stand. Oh, you have to have that wire hanging on it. So you are putting one or two coils like that. That's all. Yeah, but this is the conducting rod. This is only a rod. This is only a wire for it to hold. It's a conducting wire. That's all. Our experiment is based only on this rod. Okay, not on this wire which is holding it here. No. Okay. Did you all finish writing?
Yes.
Okay. Are we clear about this now? No more confusion? Okay. Now coming back again to the basic electric circuit diagram. Now pay attention. We know the direction of the current by looking at the positive and the negative terminals of the battery. Okay. So what do we say? It is from the positive to the negative terminal. Now what is flowing? It is the direction of the conventional current. Pay attention. Switch it off.
हमने जब बोला था
After some time we'll switch it on because it's very warm. Okay, for 10 minutes we'll keep it off and then again we'll switch
Yes.
it on. Or I'll switch on all the fans.
yes ma'am
Something, there should be some circuit.
yes no fan
Okay, let's wait for 10 minutes. So we said the direction of the current is known. But what is conventional current? It's nothing but the movement of the electrons. Now remember, electrons are moving in this direction. Okay, right? But what about the positive, what about the conventional current? It is always from positive to the negative. Okay, so the direction of the current and the direction of the electron is in the opposite direction. Did you notice that? Why was this confusion? Because in the earlier days, okay, the structure of the atom was not known. So they did not know anything about the positive nucleus, they did not know about the electrons, right? So initially, the scientists thought that it was the movement of the positive charge. So this is the positive charge is moving, and that is how the current is moving. So that is why that's why we call it as a direction of the conventional current. But actually what is happening? It is the movement of the electrons which is taking place in the opposite direction. Why I'm bringing this fact again is because in many of the questions that you will be asked here is they may not tell you the direction of the current. They will tell you the direction of the electrons. So what should you think? If the direction of the electron is given, the direction of the current will become the opposite way. Have you followed what I'm saying?
Yes, ma'am.
Suppose they are saying the direction now I'm facing, so that it becomes easy for you to understand. Suppose they are saying the direction of the electrons is from west to east. Okay? What does it mean? How
East
is
to
that?
west.
Yes. So we have to keep our hand this way. Did you understand? To understand the direction of the force. Have you got it? Okay. Now where is this given? Is once again, if you go back, come to the chapter on electricity. Go back, page number 171. 171, the last para there, last few lines. Yes. Yeah, Dekha? Yeah? Okay. Yes. How do we express electric current? That paragraph, the last few, somewhere in the middle. In circuits. Okay, let's see. The electric current is expressed by the amount of the charge. Okay, it is the rate of flow of electric charges. In circuits using metallic wires, electrons constitute the flow of current. We have marked that, isn't it? However, from there, pay attention. Electrons were not known at the time when the phenomena of electricity was first observed. Okay, that is way back in 1700 and 1800. Even the structure of the atom was not known. Okay, but they had discovered the concept of electricity. So, the electric current was considered to be the flow of positive charges. Now, did you understand what I'm saying? Okay, it was considered to be the flow of positive charges, and the direction of the flow of positive charges was taken to be the direction of the electric current. Raj, where's your textbook? What is happening down there? Then, have you followed? Okay. So, are the positive charges actually moving? Positive charges will not move because the positive charges are present inside the nucleus. Okay. So, they do not move. Conventionally, what is conventionally? So, we are talking about the conventional electricity. In an electric circuit, the direction of the electric current is taken as opposite to the direction of the flow of electrons, which are negative charges. Have you followed what I'm saying? Make a note of it in your notebook. Come on, quickly. Okay. It's not as a question, but more as a note. I want you to take it down. Explain the direction. Explain the direction of conventional current and about the flow of electrons and about the direction of the flow of electrons
Conventional current.
and the direction of the flow of electrons. Just write down on the top, refer page number 171, textbook. Okay, so this is with respect to that one. Ready? First point. Electric current is the rate of flow of electric charges. Next point. In metallic wires, electrons constitute the flow of charges. Constitute the flow of charges. Next point. However, electrons were not known at the time when electricity was first observed. Next point. So, electric current was considered to be the flow of positive charges and the direction of flow of positive charges, the direction of flow of positive charges was taken as the direction of electric current. Positive charges was taken to be the direction of electric current. Last point. Last point. Conventionally, in an electric circuit, the direction of electric current is taken as opposite to the direction of the flow of electrons, Cover your mouth, please. Okay. Electrons. Is that okay? We know that electrons are negatively charged. I don't want to put that. Take down that to remember. I is in one direction, E is in the other direction. Not the diagram, just the direction of current and direction of electron in opposite directions. For you to remember that, so nothing else. Now we come back again to this chapter and come to the page where we are talking. Example 12.2. In-text question. Below left hand Fleming. See the first one. Arushi,
Devices that are
over again. Example.
An electron enters a magnetic field at right angles to it, as shown in the figure 12.14. The direction of force acting on the electrons will be A to the right.
Try to understand the question. क्या क्या दिया है? Electron is entering. Magnetic field direction is already given. So what should you find out?
The direction.
Direction of
Force
force. Direction of force we do not know. Do we know the direction of the magnetic field? Yes. Do we know the direction of current, conventional current? Yes or no? How? What is I given? Is I given? No, I is not given. What is given?
Electrons are given as opposite.
Yes, electron is given. So you should consider the opposite direction for I. And we follow. Then we can find out F. So let's see. Magnetic field F, B, and I. So B is in this direction, right? Okay. I is coming in this direction. Electrons they are showing in this direction, but I don't want electrons in this direction, so I have to turn it here. So how is my thumb turning? It is going in. Can you understand? So what will be the option there? What is the option?
Into the base.
From here.
Yes, ma'am.
Shut it off and switch on the fan. For some time.
हम मीटिंग to call वैसे भैया
बाद में बात. अब वो बात कर रहे हैं. It's a big racket. Did you understand? No or yes? How many of you followed what is the question and how to answer it?
Yes.
Got it? Yes? Chalo, likho. Please write down this. You want to write or no? Okay, it's given already there. Just look at the other question there. Understood the question. See the next question. Read the next question. Which of the following property?
Which are the property of protons and change rise and moves in each magnetic field? There may be more than one mass velocity speed.
So what are we talking about? Proton is positive. So positive, what does it relate to? It is nothing but a current. Okay? It's obviously a charged particle, but when it is entering into what? A magnetic field. Okay? So what can increase? Speed, that is the velocity is increasing, the momentum will also increase. Because momentum is equal to P is equal to mv. So there are two options where you have got yes, the speed, velocity and momentum. We talk about velocity because it is a vector quantity. So do you understand?
How do we think the displacement of dot change?
Look at the next question. She's reading out the next question.
Current change is increased. A stronger horseshoe magnet is used, and rest of the rod
What is the question asking?
how do we think the displacement of dot AB will be affected? Current in dot AB is increased. Second, a stronger horseshoe magnet is used, and third, depth of the rod
If we get less or if we get more.
more
In which case?
in all cases.
In all cases.
First and second.
What is the third one? What is the third one?
Ma'am, in all the cases,
You are perfectly alright. And you said the correct answer. You're right. You also said, all of you said the correct answer. Because I've already dictated this answer for you. 3 cases. How do we increase the deflection? By increasing the current, stronger magnet, and increasing the length of the rod. So all the 3 cases we are that we can see. Is that okay? Here? Okay. Now. See the third one, it's tricky, huh? It's very tricky. Let me see how you can answer.
The direction of magnetic field is towards south, towards east, downward, up.
First you find out of the three things what are the two things that is given to us.
The positively charged
Cause alpha particles. So what does it tell us? Is it the current or should we change the direction? No. Alpha particle is the correct one. It is the correct one. अगर electron है तो we have to change the direction. But it is the positive part. But we don't have. The three of you heard? The three of you have finished your discussion because we are discussing something else. So as a class, all of us are discussing something else. You people are discussing something else. Is that over? Discussion is over. Now, what is the answer? Manish, thinking. Tell me what is the answer. Direction of the magnetic field. They're asking you magnetic field. Which is the magnetic field? ये वाला. हाँ. ये वाला is magnetic field. Is it south, east, down? The direction of we are talking about the D, F, B, I. So we are talking about the direction of the magnetic field. How is it going? It's a positively charged particle. That means the direction of the current. It is towards west. So like that, it's passing towards the west. And it is deflected towards the north. Deflection, that means the deflection is there. It is upward. A deflection will come outward. Keep all three of it probably. What are we thinking? Force, no? Force is upward. Got it? Yes. So such type of questions are usually asked. See now, I'm having to ask this so that it is easy for you to see, right? F, B, and I. Current is in which direction? You see which direction it is. Okay. The positively charged alpha particles projected towards west. It is projected towards the west. So it is like this. Okay. It is directed towards north by a magnetic field. So magnetic field F. This is F, B. Okay. And the direction of the magnetic field is what they are talking. So it is deflected. That means it is the force which is directed towards the north. So it is like this. So this will be upward, like this. Did you see that? What's happening here? Did you understand? What have we used? Just a safety pin here to support what type of a coil is this? This is a solenoid. Did you understand? So a solenoid, when you are passing current, it's developing a magnetic field. And what have I kept here? It's a small button. It's a fridge magnet adapter. So it's creating a magnetic field. What's happening? Because of the repulsion, you will find that this keeps on rotating. Do you understand? It's a simple demonstration to see how actually it is creating a force. Right? So a force is created on a conducting wire through which current is passing. That itself is developing a magnetic field. This is coming under the influence of another magnet which we have kept here. So that basically is possible. You can do this at home. Right? The first time I tried to do it, it did not come out. Then again I had to do it once again. So use a thin wire, probably it will work. See? There's nothing which is rotating it. It's only the force of the magnetic field which is actually giving about the question. Are we done? Here till here? Okay. Look at the last page. Last page in the set, where we have the exercise.
Yes.
Here again, so many of the questions, I think at least about 4 pages have been deleted from the new text. We had motor, we had generator, and there was a lot about electrical circuits. Everything has been cancelled. Another huge topic which was periodic table, that also is cancelled. Did you see the result?
Yes, ma'am.
God. Five times, because now, why I'm telling you this is because they have cancelled that part of a good portion, at least about, I should say about 20% they have reduced. So whatever is remaining, you better do thoroughly, because they can ask it from any part. You understand? That's why in each word, each sentence, I'm stressing, making you read, repeating the same thing over and over so that you people pay attention. And I told you in the first class itself, 90% of your learning takes place in the class if you are attentive. You understand? If you are attentive, 90% of your learning takes place in the class itself. A little bit you have to be there first. And it is easier for you to start preparing now itself, where you have not much happening at school. Is that okay? Sure. Right now, this pick up question number 4, exercise.
Do you know one result?
Wagmai? Why? You know Wagmai?
Yes.
Oh, no.
I'm asking.
No, I have not yet seen the list. We have not yet gotten the list. Who's your friend?
Yes, ma'am. Any of us? Devanshu got 92.5.
How much did you get?
Devanshu got 82.5. Shasta got 92.
Ah, that's good. Okay, this is over now?
We had to see.
Okay. Okay, let's go there.
Name.
हमारे team में हमारे team में
80%.
Abhishek was in Reliance, no?
No, Abhishek was in Podar.
Was in Kotar?
Yes, ma'am. Yes, ma'am. Was in
Wangmai, I don't know how much it's got. Kaushik, Virat. Asta, you said 92?
I think Bhavna has got 71%.
Okay. Rudra, any idea of Rudra?
No.
He was doing very well. I don't know how much he got. He was doing very well.
वो जो रहता है ना
Divyanshu?
ग्रीन हाउस 82.5
हाँ?
82.5
Dufran, any idea? Dufran was also doing very well. Rajdeep was there, Omega, Arya. Not yet got the list. Okay, children, I hope you people do well because it looks like CBSE is also tightening up their type of questions and also because they are checking will be a little harder because the portions they have cut down. Okay, in every chapter they have cut down quite a lot because this was pre-COVID, no? During COVID time they had deleted and again they have not introduced that. So whatever is there, they are going to be of course very strict in the corrections and also in the type of questions that they ask. Okay, so start preparing right away. Come to question number 4. Write down now quickly. It's almost time anyway. Just write the question and keep it with complete it afterwards. These 2 methods of producing magnetic fields.
Equal.
How can you produce a magnetic field?
I'm looking at the question.
Very good. You can use this notebook as a reference point for any exam. You don't have to search. What's the answer? Magnetic field. Where all can we have magnetic fields? Think about that. Produce. We have to produce, not naturally. And you can, yes, we can. Solenoid. By using a solenoid, you can produce a magnetic field. And
Horseshoe, straight conductor.
you tell me a straight conductor which is kept in a magnetic field. That we have. So two methods. Come on, write down. By using an electromagnet like a solenoid. That's your first point. Right, beta?
Electromagnet.
By using an electromagnet like a solenoid. And the second thing is by keeping a current carrying not a wire, conductor. Current carrying conductor perpendicular in a magnetic field. In a field. Don't write the fifth one, but just look and tell me what is the answer. Something what they are asking me the question. When is it maximum? When is the force maximum? This force is going to be maximum when? What?
They are perpendicular.
Yes. When the direction of the magnetic field and the direction of the current are perpendicular to each other, then the force experience is going to be the maximum. Write down. Write it properly. There's a question number. Which anyone has a volume. Give us. Okay, those of you who have volume, you can look at page number 165. 165. This is with respect to the diagram, that experiment that we have done. Okay. So I'll ask you to read it out.
Student was asked to
1 minute. Did you all get the question? A student was asked. Arush, did you get this question? 165.
The student was asked to perform an experiment to study the force on a current carrying conductor in a magnetic field. He took a small aluminum rod AB, a strong horseshoe magnet, some connecting wires, a battery, and a switch, and connected them as shown. He observed that on passing current, the rods get displaced. On reversing the direction of current, the direction of displacement also gets reversed. On the basis of an understanding of this phenomenon, answer the following questions.
So they have given you the setup. Okay. So these are some of the type of questions that you might be asked. They will give you an experimental setup. We know what is happening. So based on it, you are supposed to be answering the question. Read the first one.
State the condition under which the displacement of the rod is largest for the same magnitude of current flowing through it.
What's your answer? When is the displacement the largest if the same current is passing? When?
Force and drive is the
Ah, yes. When the direction of the current and the direction of the magnetic field are perpendicular to each other. Or you can also write when the conducting rod is kept perpendicular to the direction of the magnetic field. Did you understand? So that is when you are experiencing the maximum force. Next.
State the rule that determines the direction of the force on the conductor AB.
Pata, you tell me. State the rule. I'm asking Raj to tell. Raj, tell. What does this rule tell us? Here, Raj, this rule. Tell it in your own. Tell it. Because I've asked you to learn it up now.
Limits left hand rule.
Statement. Imagine. What are we doing? Stretch. Perpendicular. Yeah. Okay. Raj, are you listening? Because I'm asking you to say again. Then.
If the finger is showing the magnetic field,
Showing the direction.
the second finger showing the direction of current, then the thumb will show the direction of force or the motion.
Okay. Shows you the direction of the force. Okay. Have you learned it up? Did you learn? Learn? Okay, the next one. What is the next question?
If the U-shaped magnetism, particularly under aluminum rod, is suspended horizontally with its end beam towards due north, then on passing current through the rod from B to A, as shown in which direction will the rod be displaced?
Okay, now for example here, of course it's the same thing that is given in the textbook. But sometimes what happens is they might give some other direction also and then you have to use the left hand.
Yes.
Correct? Next.
Name any two devices that use current carrying conductors and magnetic field.
Follow. What are the devices? Where do we use such type of devices? See, they have already given no devices which use and all that. Where are we using? Current carrying and magnetic fields, electric motor, electric generators, loudspeaker, microphones, ammeter, voltmeter, all of them are using. See here.
Electric motor generator. Electric motor
Next.
generator.
Draw the pattern of magnetic field lines produced around a current carrying straight conductor held vertically on a horizontal cardboard. Indicate the direction of the field lines as well as the direction of current flowing through the conductor.
So which rule are we using? Which rule are we using there? Is it left hand or is it the right hand? Because direction of the current is given and the direction of the magnetic field is asked. So that we should be able to do. Okay? Is that it? If you people are going outside, make sure that you come back fast, okay?
मैं क्या बोला कुछ बोला
ज्यादा ही हो रहा है
क्या बोला?
एलियन ही है ना
अच्छे से तो बोला कर ना ये गाना मिला पूरा गाना मिला ये आयुष्मान पूरा गाना मिला अरे सैम डब्ल्यू भाई तुझको देख नहीं पाएगी मैं बता रहा हूँ इतनी घड़ी है दिखाई नहीं देती वो फ्लैश लाइट
Sangeeta, Sangeeta.
कुछ फ्रेंच टीचर का नाम संगीता
अरे डरावनी है वो छोटू
कहीं हो
भाई इतनी छोटी है
मेरी हिंदी टीचर का नाम संगीता है तू ही चिल्ला